So thank you very much for this kind introduction. So yeah, for me it was a very short trip. So we are a Berlin-based company, so it was quite easy for us to get here. So I will talk today about a topic which is quite similar to what Curious was talking about, but from the approach of the biology of multi-organ chips. So my talk is on the way to a digital twin in preclinical trials, how automation and continuous data acquisition enabled AI-based in silico models. Yeah, it's a very catchy title. So let's go to our company. So we were founded in 2010 here in Berlin. We are around 32 employees and 30 associated researchers. We have a very strong customer base since we are on the market for quite some years, so both in industry and in academia. And we have a 9 patent family with more than 140 patents so far. And we are certified for quality management as well. The problem, I think every one of us knows, is that in traditional drug testing, we have like dramatic failure rates. And tissues believe that this is because of 2 reasons. So right now, a few years ago, you could mostly do like animal models, which are human, which are not human but systemic, or you can do 2D or 3D cell cultures. These are human, but they are not systemic. So both are limited in many ways. So this led, in our opinion, to these dramatic failure rates of up to 90% for the drug development. The solution we developed is testing the patient without the patient, which means like developing a universal physiological template. So this was the idea we started with, where we have like this connection of many organs together to have this cross-organ communication and to combine it with human cells. We established several models, so here just a few of the possibilities. You can use our chips with iPSCs, you can use it with cell lines, you can use it even with biopsies, so precision medicine is definitely possible here, and we have precision cuts as well in our chips. So there are a few models you can show. And yeah, so before I go to the more technical part, let's go a little bit deeper into the chips. So we started with the chip 2, which has like 2 compartments with 2 organs in it. Then we went on to the chip 3. So both are still valid products, but the most complex product we are selling right now is the chip 4, and that's what I will talk about mostly today. So the chip 4 was the first physiologically based and fully pharmacokinetic compatible chip. It was published in 2015. And since this is the basis for everything else, I will show you a short video. So there are 2 circuits in this chip. One is the blood circuit, and then there's like an excretion circuit as well. We have a membrane in between, which is seeded with kidney cells, with dust filtration. And this is like the basic structure. This is connected to an adapter plate where we have all the tools we need to screw in compartments, insert whatever you need. You can decide it on some points. And we have, if you would cut it, we have like different applications. So this one is an example where we can do ADME, which means like we have a compartment for the intestine. We have the distribution done by our microfluidics. We have the metabolism done with liver organoids. And we have like another organ. Mostly we use brain right now, but it's possible for any other organ as well as for the kidney, for the excretion. So this is a chip. This is the basis for all the data we are getting. And if you do it manually, you have to use a device like that, which controls the pump and the flow in our chips. So we are just doing this for quite some time. It's a large customer base, and we established 10 multi-organ models which you can just buy. And if you're interested, we already have a booth here. You can just check it. But normal use is like 22 context of use assays you can do with the 2-organ, 3-organ, or 4-organ chips. And like for all of us, it was like last year was very exciting. So when the FDA Modernization Act was signed, I think this was a big moment for our whole community. And that's like a proof that what we all are doing is on the right way. So that was a very important point. But we found, in our opinion, we said, okay, we have like established organ models. It works very well. We have satisfied customers, but it's not scalable yet. So 6 years ago, oh no, it's 7 years now, we thought about, we started the automation. And the ideas behind this is that these microphysiological systems, any kind of these systems we've seen so far, have certain challenges. If you have like more complex systems, we have like more complex labor as well with them. So more complex assays, more complex data points you want to get out, and this is just not that easy if you do it manually. Okay. I mean, it's more cozy when it's dark, so it's fine for me. So yeah, what else? So there are limitations to the feeding regime. So normally I think most of us are eating 2-3 times per day. If you use the most microphysiological systems, they have like feeding every 1 or 2 days. So there are just limitations about that, and many systems are just kept in incubators, which means if you do want to make images or whatever, you have to put them out of the incubator, which is a lot of stress for the cultures. And of course, we already heard it in the talk before, there's always some user and lab dependencies. And we said, okay, let's do automation. We want to standardize. We do want to increase the throughput with that. And we want to do like a more physiological maintenance. And the most relevant one is that we want to get more data out of it. Because I had some discussions in the company from the beginning that everyone was very proud of the chips, and we should be proud of them, but nobody will take these chips and put it on a table to look at it. It's about the data the chip generates. So this always should be the most relevant part of it. So that's the device we developed. It's the Humimic Autolab. And it's the whole upper part is under a safety bench. Or maybe I do it like this so you can see it properly. We have a layer here where you can enter 24 chips, which means for the chip 2, 48 circuits of 48 tests you can do. You have tools here which do the opening, the pipetting for all the chips, which there are lasers for position tests and stuff like that. And there's like a second tool which is for our microtiter plates or for well plates. So our feeding is done through microtiter plates, so there's a fridge below, and here you can store 66 of these plates, and they are brought in an automated provisioning system to the top, and then they're pipetted, and pipetted samples are taken, then it's brought back to the fridge. This is like everything you need for handling the chips, and of course we have in this area the pumping and the heating as well. And then what's for our data aggregation, we have like a microscope below. So you can see it, our chips are completely transparent. So while they are executed, while we are doing assays, we can analyze it with images at any time. We have like bright field images, we have fluorescence images as well, because we can do like, with the dispenser, we can do stainings as well automatically, and we can do fluorescence imaging from the bottom at any time. We have different magnifications, so I think I'm in the way for that, but from 1 to 10 times magnification, and that's what we developed. So we finished with this system around 3 years ago. We have several ones at our facility. One is already at a customer, and this is what the current basis is. So to understand what data we have to talk a little bit about the workflow as well. So first you have to decide what do you want to test. In this example, I just decided that we have like a 20-day assay with intestine and liver. Then there's like a software where you can just enter all the data, because for the data science we do afterwards, it's important that we know which kinds of organate, which kinds of liquids are entered there, and so we need all this data so we can process it later. So there's like a planning software for that. And then this planning software creates a command list which is executed by the system. And what we get then is like a lot of data from image analysis. We have a lot of data from our samples, so chemical data like LDH, glucose, and so on. And this is what we are using for the analyzation. And what's getting more and more relevant is this feedback loop. So we want to take this data more and more in real time and change or do predictions about how assays can go, what to change to make them most effective. So let's go deeper into the data we have available. So this, of course, we know our chips, which kind of inserts are in there and everything else. It has to be entered. We have the organoid information. We have our liquid and medium data. And of course, we have the process schedule. So we know whenever something happened at a certain time point, we have liquid application of some substances, so we know all that. And on the other side, we have the measure data from our pumping system, from the heating system as well. So this is some data we just have provided by the machine directly. Then we have the microscope, and there we have, with image analysis, a lot of opportunities. So this is just one example where we have like liver spheroids, and this is like image segmentation to detect the liver spheroids. And of course, we can detect factors like circularity, degradation, growth, but this values on its own doesn't matter much. We need the gradient between the different days, and so that's why it's important that we can take images whenever, how often we want, and this is like the big benefit here. I said it before, so yeah, so this is just one example. So this is the movement of the spheroids. We just get it out of our positioning data. We will see if this is very relevant, but we definitely can get some simulations for the flow, or we can combine it with the simulations for the flow as well. We have daily changes from the solidity of our spheroids. And in case when we do fluorescence imaging, we have like pH, heat maps, O2 concentrations as well. And this is this image here. I think only half of you can see it, but what we have here is 20 times magnification of the spheroids, and we have this small beads, and they are fluorescenting depending on the pH value or depending on the O2 concentration, and that's how we create this heat map where we know in which area of the compartment, in which area of the chip we have which pH value or O2 concentration, and this is like data density which was not possible before. And then we said, okay, what else can we do with that? We have this microscope, we can take like thousands of image pairs, and we just started, this one was 3 years ago, we started with endothelial cells because we have these channels between the compartments. They are quite small, and they are, in many experiments, they are endothelialized. And this can be made visible with fluorescence very easy. So this is like the image pair. So this is bright field imaging, this is fluorescence imaging, and at the top, I mean, on the beamer it's not very good to see, but it's possible to count, to see the cells here, and to evaluate it with machine learning. On the bottom image, it's not possible at all. So when you want to see this bottom image, you have to do like a staining, and then you have disadvantages like phototoxicity, extra time, extra money. And we said, let's take thousands of these pairs and try to simulate the staining. That's what we have done. So on the left side, you see the bright field image. On the right side, so you see the prediction. So now it looks a little bit more like the fluorescence image, but if you overlay it with a real fluorescence image, we get like a pretty nice prediction. So we can see values like technical values which are very relevant for me, which I want to have as time series data for the number and the size of the cells, the orientations, the density of the cells of the whole area. So this is what we get out of it. So I was very happy with that. I showed it to our biologists. They said, oh, that sounds nice, but it doesn't look like a staining. So okay, let's try to do like a staining, not for the technical people, because this is fine for me, but just for the normal use, what they are used to. So what we did here, we put in our bright field images, we used our fluorescence images again, and all of this, by the way, was done completely automatically. So there was no human necessary to label where's the cell, where's no cell. So this is all done because we have the data of positions and everything in our automation system. And yeah, and one of these images I will show you in a second is the AI-generated one, and the other one is the real one. And we were able to fool quite a lot of people with that, and they said, okay, this looks like we are used to, so I like that. Right now we are using both, one just for publications and so on, and the other one is for technical evaluation, much better for us. So we have both pipelines equally used. Yeah, but this is just one of the possibilities we just can do with this kind of software sensors. And what's the next step right now is that we are here. So we have our automation, it's established, it's yeah, working very well. We have our chip 4, which is used since 7 years, 8 years, I think. So we have a lot of experience with it as well. We have an own stem cell database where we can do our iPSC cells. So this is like the starting point. The information sources we have available are very interesting as well, because with omics we can get a lot of data from the stem cells and for predicting behavior and stuff like that. We have like the real-time data of the imaging. We have our time series data, which can be like this temperature data, or from software sensors like endothelia, flow data, whatever we can generate out of our pipelines, we have that as well. And we have the experience with the chips. We know the schedule of any liquid, of the kind of liquid what was added, and in some cases where we do like drug repurposing, we even have like the clinical data. And this is what we are using and entering into our models. So we have, for example, a PBPK model, which is like simplified, shown here. We have like flow simulations of our chips, and we are now on the way to combining all these to generate like a digital twin of our chip. So we want to do like a simulation, what will happen in this chip before we do the experiment. And in the beginning, of course, you get some values of it. So maybe you can do like prognosis, treatment decisions, whatever, but the results in the beginning, they will be not very good, because the amount of data we have is not enough right now. But that's the reason why this is a circuit. So we are connecting it directly to our automation system, doing predictions, executing the real assay, biology assay with our chips, comparing it with the predictions, and this is how we think. So this is not existing 100% right now. It's on in the working right now. So this is how we want to go to a better and better digital twin, and there we need like a lot of different additional data sources as well. So this is how we want to go to a digital twin in preclinical trials. And as soon as we achieved the simulation of the chip 2, we want to go to the more complex chips, so like a chip XX or XY, where you have like 10 to 20 organs, which is like the direct step to the human. And I think that's a very important thing, because I mean, this is a very, very complex system. But right now, there's like a big part in the simulation community which tries to simulate the human completely just from real world data. And this is like a very interesting approach. But due to the noise in biology, I don't think you can work with real data. You have to have something which you can replicate, where you can do like 10, 20 chips of the same kind to reduce the noise of your data. So that's why we believe simulating, starting with the chip, with the simpler systems than a human, is the only way to go forward in that area. But of course, the final goal is to simulate the complete human. This is a very, very big project. If you are interested in that, if we are interested in sharing the data or to partner with us, definitely come to us. We have a booth as well. Join us at booth 1. There are a lot of work we have to do in the next years to come to this vision, but I think it's definitely worth it. I haven't shown much of biology data. There are several other presentations from my colleagues from the biology department where you can go and see several posters. Tomorrow I think my colleague Ilka is talking as well. So if you want to see some biology data of our chips, of our automation system, just go to the posters, come to the booth, and if there are any more questions, feel free to ask. So thank you very much.
Thank you. I think we have time for one economically worded question. Going once. Okay, I'll have a quick question for you then. In terms of trying to pull human data in and put that in your system, that is extraordinarily noisy data. How do you ensure that that does not taint your AI? Because that is famously difficult to work with.
So currently we are really working just with the data of the chip. So for that reason, because it makes much more sense for us now to, at this stage, to work with the chip data. Yeah. So basically that's the answer.
At some point you have to...
We definitely have to, but there's like a big benefit of this system, because if you have a prediction, and maybe it's not that easy to explain this prediction, but we can just execute the test with our chip, and then we see if the prediction is right, because we have like biology results. We don't have to trust the informatics or the AI only, because we can just execute it and say, okay, this is promising, let's do it. Okay, it's showing the same results as predicted, and then we can go to the next step.
Thank you.
Yes.